All right. Okay. So we'll take a look at today's content. And so on Tuesday, we covered ordinary least squares regression in matrix notation. And we said the way we're going to do this is, we describe, we're going to present the prediction of values using linear regression as a set of matrix operations. So traditionally you would say, okay, your linear regression line is the intercept plus the slope times x. And here where we're going to take our intercept and slope parameters and put them into this vector w. And then we multiply that by our x values, and we're going to say our prediction is going to be w times x, right? And we said in order to kind of solve this, we need to take gradients or derivatives with respect to our vectors. And so the values here represent scalar values. W transpose x is a scalar value, x transpose w is a scalar value, w transpose w is scalar, and even w transpose some symmetric matrix C times w is also a scalar value. And anytime you take the gradient of a scalar value with respect to a vector, you are going to get a vector. You're going to get a vector, basically the vector of partial derivatives. And so these are some useful gradient relations. If you take the gradient of w transpose x with respect to w, you're going to get x, and you're going to get all of these things. And so on Tuesday, we talked about the OLS loss function, the loss function being the squares of the residuals, and we said the squares of the residuals can be expressed as the set of matrix operations. So basically, we're going to take the difference between the actual value, our target value, t, minus what our predicted value is, w transpose x. So it's t minus w transpose x, and we're going to square that thing. So it's t minus w transpose x transpose times t minus w transpose x. And if you expand that out, you're going to get t transpose t, w transpose x transpose t, and w transpose x 2 minus 2w transpose x transpose t, and plus w transpose x transpose x w. And in our things, we are looking at the mean squared error, so we're dividing all of these things by n. And so we said if we want to take our loss function and take the gradient of the loss function, we'll take this, the gradient of this with respect to w, and we're going to set that thing equal to 0, and we're going to solve for where the gradient or the derivative is equal to 0. And that's going to give us basically a local maximum or local minimum, and in our case, we get a local minimum. And that's kind of how we optimize functions. So the gradient or the derivative L with respect to this 2 by 1 vector is going to be a 2 by 1 vector. And there's no w terms here, so we get a 0. W transpose x transpose t with the gradient of this with respect to w is going to just be x transpose t. And over here we get x transpose x w times 2. We set this equal to 0, and then we're going to solve for w. And when we do that, we end up getting this solution, x transpose x inverse x transpose t. And that is our solution for what w is, the set of slope and intercept parameters that will minimize the squares of the residuals, x transpose x inverse x transpose t. And I think this is where we left off on Tuesday. Okay, so this is the estimates of our intercept and slope that will minimize ordinary least squares regression. All right, so here is just a very simple example of us running this through. All right, so here I have a vector of x, 1, 2, 3, 4. T has the values 1, 3, 2, 4, and this is the plot of the points. So we've got 1, 1, 2, 3, 3, 2, and 4, 4. And the question is, what is the line of best fit, the line that is going to minimize the squared residuals, right? Well, using our solution from back here, we'll take our x transpose x inverse times x transpose t, and we will solve for what our intercept and our slope should be. So our x matrix, remember, we're going to take our vector x, 1, 2, 3, 4, and bind it with a column of 1s. So our x matrix is going to be 4 by 2, okay? Again, because the intercept is a constant being added to all of our things, and so basically when you do your matrix multiplication, you want to add 1 times your intercept to all of these things. So here is my matrix X, and if I do X transpose X, all right, so here I have a 4 by 2 column, or 4 by 2 matrix. X transpose X will be a 2 by 2 matrix. And we're going to do X transpose X inverse, X transpose T. So X transpose X inverse, the inverse of X transpose X, the inverse of this thing is, such that this multiplied by the next thing ends up being the identity matrix, and this is what our inverse matrix is. So this is X transpose X inverse. And just kind of going along, X transpose X inverse, X transpose is the next thing. So I'm taking this 2 by 2 matrix and I'm multiplying it by the transpose of X. So again, X is a 4 by 2, so the transpose is going to be 2 by 4. And if I take a 2 by 2 matrix multiplied by a 2 by 4 matrix, I still have a 2 by 4 matrix. So here I have X transpose X inverse, X transpose, and now I will multiply this by the matrix T. Okay, so the matrix T is n by 1. We have 4 observations, 1 column. So I'm multiplying a 2 by 4. I'm going to multiply it by T, which is 4 by 1. And so that will result in a 2 by 1 matrix. So I'm going to do X transpose X inverse, X transpose times T. And this results in my 2 by 1 matrix, which represents the intercept and the slope. So the W hats that I get, it says the intercept is 0.5 and the slope is 0.8. So that would be the solution for the line that minimizes the sum of squared residuals. An intercept of 0.5 and a slope of 0.8. And that's just doing X transpose X inverse, X transpose times T. So I'm just doing these matrix operations to get the solution for our intercept and our slope. And likewise, if I run R and I just do LM and I say, give me a linear model where you're predicting T based on X, it gives you the intercept and the slope, and it says the intercept is 0.5 and the slope is 0.8. And that matches what we got. Okay, so by doing our matrix operations, we get the same solution that R's LM function gives us, so that's a good sign. Okay, and if you wanted to make predictions now, the predicted values, you would take your input X matrix and you'd multiply it by the W hat that we just estimated, right? So our W hat is 2 by 1. We would take our X matrix, which is 4 by 2, and multiply it by 2 by 1. So 4 by 2 times a 2 by 1 will give me just a 4 by 1 matrix. And this is just the column of predicted values. So it's predicting 1.3, 2.1, 2.9, and 3.7. And if I plot that, this is what it looks like. So for the value 1, remember we have this intercept of 0.5 and slope of 0.8. So we're predicting 1.3. The actual value was 1. The next value is 2. With a slope of 0.8, we predict 2.1 and the actual value is 3. Over here we're predicting 2.9. Okay, we're predicting 2.9. The actual value is 2. We're predicting 3.7. The actual value is 4. Yeah, question?
Is there a reason why you use W hat notation instead of like Y hat notation?
Well, W hat is the estimated intercept and the slope. Okay, And here, the predicted values are t hat. So is there a reason why I'm using t rather than y? And that's just to kind of follow the textbook's notation, where instead of using y, they use t. T standing for target value. So
also w hat here is the beta.
The w hat would be your betas. Yeah, w hat. So normally, yeah, traditionally you have beta 0 and beta 1. We gather those values into a vector, and we could have a beta vector, but our textbook uses the letter w rather than beta. W just a generic term for weights, because we're going to have all sorts of, I guess you could have other kinds of models where you have different weight values, and so you can, so anyway, this w represents the vector of parameters, in our case an intercept and a slope, and we call it w hat. Right? Okay, so this is our actual values in black, the predicted values in red, and we can see, yeah, indeed, they form a straight line. Okay? So that's ordinary least squares regression, and I think, I imagine a lot of us are already kind of familiar with this. Let's try this out for some data here. So here I have the Olympic 100-meter dash data. Okay, so this is the winning times for the Olympics, and this is what it looks like. And so I could ask R's built-in linear model function to say, hey, give me the intercept and give me the slope. And it says the intercept is 36.3. What is the interpretation of the intercept here? So what is your x-axis? Your x variable is the year, and the y that we're predicting is the winning race time for the 100 meters. So what is the intercept? Intercept of 36. Yeah.
Does it mean year 0?
Yeah, so if we had an Olympics event in the year 0, so 2,000 years ago, I guess, 2022 years ago, we had an Olympics event, and assuming this is how fast people could run, this would be the winning race time. Now, of course, that doesn't make sense, right? It's the grave error that we would have committed in this case was extrapolating our data, and so extrapolating. So a linear model might make sense for between the years 1900 and 2000. But trying to extrapolate this 2,000 years into the past is a silly mistake to assume that this linear trend would continue 2,000 years back, right? And you could even go further back to like when the ancient pyramids of Egypt were built and things like that, right? That's like another thousands of years back. And that would be... our winning race time would be even slower, okay? And then again, it would also be very silly to project this far into the future, where eventually we would have race times of 0 or negative values, okay? But maybe it makes sense here. And this slope here is negative 0.01328, meaning every year that goes by, we're expecting the winning race time to get basically 1/100th of a second faster, okay? Or maybe a little more than 1/100th of a second, okay? 1.4, 1.38, 1.33 hundredths of a second. Okay, so our X matrix here, how do we get this? Well, we can do the same thing. X transpose X inverse, X transpose T. Our X matrix now is a column of 1s and a column of X's, okay? And we would take this and we would do X transpose X inverse, X transpose T, and I won't go through all of the steps, but again, even though we now have, I think it's 28 by 2, 28 rows here, when you do X transpose X, you're going to get a 2 by 2. The inverse of that's 2 by 2. You multiply that by the transpose of X, you'll get a 28 by 2. You multiply that by T, a 28 by 1, and you're going to get a 2 by 1. So, or 2 by 28. So now we get a 2 by 1 matrix. This is the intercept, 36.309. slope of negative 0.01327. And we can see these are the exact same values, 36.309 and negative 0.01328. We have that, 36.309, negative 0.0132. And here, I guess it has a few more decimals. Instead of 8, we have 7.5, so on and so forth. So these values for the intercept and the slope do indeed match the values output by ln, okay? Just by doing kind of our matrix operations. And again, we can do our predicted values by taking our X matrix and multiplying it by our vector W hat. And we get all of these predicted values here. Okay. And here is the plot of the linear regression line in our data here. All right, what if we want a non-linear response? What if we want a non-linear response? So what if we wanted to fit something other than a straight line? Okay, so we look at this and go, oh, maybe I need to have a little bit of curvature or something. Okay, we could try adding basically a non-linear term. We could do polynomial regression, and so I could create my X matrix. Currently, I have a column of 1s and a column of X values, and I could expand this by adding a third column. And I could take each of these X values and I can just square them, right? So I'm going to have the value X1, I guess the year 1900, and then this value would be 1900 squared. And I got 1904 and then 1904 squared, whatever that is, okay? And we would go through and do that. And so here, this is kind of what our column, the first 6 rows of our column, I've got, I guess my first year was 1896. So 1896 squared is, what is that? 3,594,816. 1900, 3,610,000, so on and so forth. So this is what our matrix now looks like. So the dimensions of this matrix, we have 28 rows, and now we have 3 columns. It's 28 by 3. And so our W vector, we now have 3 values in our W vector. We're going to have the intercept, the slope for x, and basically the coefficient for x squared. So we're going to have 3 values in our W, right? Or if you think about your beta coefficients, how many coefficients do you have? You're going to have an intercept, the slope that corresponds to x, and then the coefficient that corresponds to x squared. Okay, so here we have these values, W0, W1, and W2. But we can still represent it as just W transpose X. Okay, we can still, if we gather the 3 W terms into one vector, we can still represent our predicted value as W transpose X, right? Because X is still 1, X, and X squared. And if I multiply that by the vector W transpose, this is the same value. Okay. So again, our data is just X times W, and you can see that indeed, if you take any of our values, X and W, and so you have the first element here multiplied by this times this, and this times this, you're going to get the exact values that we have, W0 plus W1 X1 plus W2 X1 squared, and so on and so forth, and that's exactly what we want. And so our predicted values are X times W, and our loss function is still exactly the same. The target value, the actual target value minus XW, and we're going to square that. So T minus XW transpose times T minus XW, and if I can multiply that by the constant 1 over n, that will give me the mean squared error. And so even though I added terms to my X matrix and I added terms to my W vector, the notation and the formula here in matrix notation is exactly identical as what it used to be, right? Whereas if we were to try to solve this using partial derivatives, now we would have a system of 3 equations. We have 3 unknowns, a W0, a W1, and a W2. And I would have 3 kind of equations, 3 partial derivatives, and I would have to kind of solve a system of simultaneous equations there, which would be, you could turn it into the matrix equivalent, but basically it's a little bit more tedious. Whereas, solving for the partial derivatives for the intercept and the slope, it's a bit of work, but it can be done. But you can understand as you would add more terms to your linear regression model, it gets kind of more and more cumbersome and tedious to solve. And so this is where using matrix notation helps us and speeds things up. Okay, there is a little bit of a leap to go from kind of just individual terms and partial derivatives, getting it into matrix notation. But once you get into matrix notation, you can start expanding it and you don't have to worry about things, okay? Because it's all kind of handled in here. And so because this part is exactly the same, I can skip all of the work. I mean, we could go through the work and it's going to be exactly the same, right? When I expand this, so here we're on slide 26, but when I expand that, we would get this exact thing. And when we go through the process of solving, taking the gradient of this with respect to W, we would get this exact thing. And when we solve for W, we would get this exact thing, okay? Because this part is exactly the same as what I have here, and once I expand that, I'm going to get exactly what I had on that first slide there, okay? So we could go through the process and we would arrive at the same exact solution, where W hat is X transpose X inverse X transpose T. And basically, I hope this is starting to give you a glimpse into why, at kind of these higher levels of statistics, we love working in matrix notation rather than kind of individual, writing everything out individually and, trying to solve for W0 and W1 and W2 separately. We like to work in matrix notation, and we get to kind of do this. So lots of matrix operations we will be encountering in this class. Okay, and so the best estimates for this is going to be this. Okay, so far so good. All right, let me go ahead and give you your first view quiz answer for today. So week 1 Thursday, I think, is that visible? Is the letter E. E as in elephant. E as in elephant is your first view quiz answer for today. E. All right. So I take my matrix X and I say, all right, let's get our coefficients then. So I do X transpose X inverse, and I say solve X transpose X inverse to get the inverse, right? X transpose times X, solve gives me the inverse, times X transpose times basically my matrix T. I take the column of Olympic times and I turn it into a matrix. But then I get an error. It says error in solve dot default X transpose times X. System is computationally singular. What's going on here? This, if you look at this command in here, it's pretty much the same as what I did here, right? So here I did X transpose X inverse, or solve, times X transpose times, take the times and make a matrix out of them. And I got it, okay? And that was just for one column of ones and the year. And over here I expanded it by taking the year, the column, and the year squared. And when I do the same command here, I now get an error. Any idea why we're encountering this error? Yeah. The inverse matrix does not exist. So that is what this is saying. Okay, it says when we tried to inverse it, right? So the error message is informative, right? So the solve is for when we do the inverse, and it says system is computationally singular, and we know that that's what happens when the inverse doesn't exist. Okay, but is it true that the inverse doesn't exist? It's actually not true. The inverse does exist for this matrix. It's just our computer is running into problems. Okay, so maybe if I show you what X transpose X looks like, can you imagine why it might think that the inverse doesn't exist? Okay, so part of the problem is, so everybody took 102A, right? And I don't know if you took it with me, but did you guys talk about floating point math? Okay, and what does machine epsilon mean? What's machine epsilon on your computer? Everybody's got the same machine epsilon, pretty much. Two to the negative 52. All right. Okay. Well, anyway, so the way we represent numbers on the computer is we're not working with real numbers, right? Like real numbers, there's infinitely many values between 0 and 1, and infinitely many values between 1 and 100, and things like that, and the same infinities. And we just can't represent infinite numbers, right? Pi has infinitely many digits after the decimal, at least we're assuming so. And you know, you can't represent pi exactly on the computer. We just kind of truncate it and say, hey, this is 16 digits of pi, and that's close enough for pretty much all practical purposes ever, but it's not the exact value of pi, and that's fine. Okay, basically when we do when we take the year squared, okay, we're dealing with these huge numbers, 3 million or something, okay? And if I take this and I do X transpose X, I get this big number, okay? 4 times 10 to the 14th power, I get this huge thing. And when I try to inverse this, value, okay, and I don't remember exactly how to invert a 3 by 3 matrix, but you know, there's a thing, right? And basically with these huge numbers, now we're going to be dividing by a huge number, and we're going to be running up against the machine epsilon. We're going to be running up against the issue where now we're dealing with such a small number that we can't distinguish between, say, 1 plus you know, epsilon, right? Because they're too close to each other on the number line, and the computer can't tell these things apart. Okay, so that's kind of the issue here, right? One of the columns, like, so if you take the year 2000 and you square that, you get 4 million, and then when you do, you know, X transpose X, you get this 10 to the 14th value, and finding the inverse, which involves dealing with the determinant, ends up getting a value that's really small, okay, something smaller than machine epsilon, and we get this error because of computational instability, right? And the computer says the inverse of this matrix doesn't exist, but that's actually not true. The inverse of the matrix does exist. It's just our computer can't figure it out because we're dealing with numbers that are too big, or, you know, once we divide it, now we're dealing with numbers that are too small. Okay, and so machine epsilon is basically, you know, if you're looking at the number 1, what's the next value that the computer can distinguish from 1, right? And so, you know, in real numbers, you can go from 1 plus, you know, 1.000. You can have like 100 decimal zeros and then a 1, and those are distinct values. But the computer can't tell those apart because that's too many. Computer can only really establish maybe 16 places behind the decimal, and if you try to, you know, add 1 plus 10 to the negative 18, it can't do it, right? It can do 1 plus 10 to the negative 16-ish, something around there. But even then, it's going to be inexact, and we run into error things. Okay, so one way to kind of just work around this, and there's lots of workarounds. But one is you just say, okay, well, let's make our numbers smaller, so we're not dealing with 10 to the 14. So I'm going to take, so when I create my X matrix, I'll take the column of 1s, I'll take my column of X's, and then I'm going to do X squared, but I'm going to multiply it by 0.0001. Okay, so same values, but I'm just moving the decimal 4 places over to the left. And now that I have this column, so basically it's the same as this matrix. All I've done is I've just moved the decimal of this thing. I've just scaled this last column here. And now that I've done this, I can do X transpose X inverse. So I'm going to call this matrix X scaled. And I do X transpose X inverse, X transpose this, and it works. Okay, it is able to find the inverse of this matrix, X transpose X inverse. Then it can multiply by the X transpose of X and do this. And it can give us the intercept and the slope for X and the slope for X, the coefficient for X squared. Okay, it's just that this one is off by a factor of 0.0001. Okay, so we have that. Okay, does that kind of make sense? What's going on here? And so these are things that we kind of have to keep in mind as well. A lot of times we treat the computer as being able to handle all of our numbers, but there are a lot of times and instances where we do run into kind of the wall of our computer's computational abilities. Okay, and there, this is just one simple workaround, and there's a lot of other things that you could be doing to kind of avoid running into the problem of when your computer is no longer able to handle these big numbers or really small numbers. Okay, so if we did this, we can also ask R to calculate the coefficients from our linear model, and we can say, all right, predict time based on the columns in our X matrix, and here we'll have our X scaled matrix. And so here I'll do time tilde X scaled. Now, normally R will fit an intercept plus the kind of coefficients for any column in your X matrix. But in our case, our X matrix already contains a column of 1s, so we don't need to fit a separate intercept term, because the coefficients for each column will include that coefficient there. So we do so we include a 0 plus. Okay, so I can do predict time based on the X matrix, and I do a 0 plus to avoid fitting a separate intercept term. So anyway, it finds coefficients for each column in our X matrix, and we have that. Okay. And so when we do this, we get the intercept, the X slope for the X variable, and the slope for the X squared variable, and we see that they match these values exactly: 396.328, negative 0.382, 0.944, 396.328, negative 0.382, and 0.944. Yeah, question?
If you did not have the 0 there, and instead just like extracted the 2 columns without the 1 column, would it produce the same output as well?
Yeah. So, so if you don't put the 0 there, and you put in the matrix where you have a column of 1s, R will fit the intercept term, and then you'll get kind of this error for the column of 1s, because you'll have basically this computationally singular thing. So you'll get like kind of an unknown value, and then you'll get these two things. If you just extract out the last 2 columns without that column of 1s, and then you leave off the 0, then yes, you'll get an intercept, and it will say intercept, and then it will have a coefficient for the other 2 columns that you've extracted. Yeah. Okay. So again, here we can do the fitted values by just taking x multiplied by w hat, right? Because that's how we're predicting our t hat values. And when we plot that, this is what we get. And so we can see, oh yeah, there is some curvature to our fit now. Okay. So now this represents kind of our quadratic fit. All right. In R, there is a function called poly. Okay. Poly will generate basically matrices of polynomial values. Okay. And so, one thing we did, to kind of work with this was we just multiplied our really big values by, some coefficient 0.0001 to kind of scale them down. But one issue with kind of just taking x and x squared is that all of those values end up kind of very, very, very highly correlated. So I don't know where the chalk is. So if you think about if this is x, x squared looks like this, and x cubed looks like this, and x to the fourth just keeps kind of getting, these all are highly correlated, right? I mean, over here maybe now you have some opposite things going on, but at least on this positive side, everything is highly correlated. And so we also know that when you have high collinearity between your predictors, that results in kind of instability of your estimates, or it leads to high variance in your coefficient estimates. And so one thing you can do is you can use this function poly. And what poly will do is it will create uncorrelated kind of polynomial values. So you can kind of isolate, is there a relationship to x squared, or is there a relationship to a third order polynomial here. So we can take just some matrix, some vector x, and we can say create a vector of the second degree. And so this first part, so it scales and transforms all of these things. And so this first part is going to be linear. And the difference between this row and this row is the same as the difference between that row and the next row, and so on and so forth. So like just to demonstrate, 0.3061317 minus the next value, 0.2851996. That's a difference of 0.0209321. And if I subtract that from 0.2851996, that should give me the next value, 0.2642675. And then I could subtract kind of the next value, 0.2538015, and we'll get that same difference. Whoops. And I did the opposite sign there, but you'd get it, the difference is basically 0.02 from here to here, 0.02 from here to here, 0.02 from here to here, so on and so forth. Okay. Although, there's a linear. Why is there? This one's like a little bit off here. But okay, but they kind of scale all of these things. I think in the original data maybe there's. Yeah, in the original data, there's a little glitch, not a glitch, but it goes, 4 years later, 4 years later, and then 2 years, and then 2 years, and then 4 years, and then 8 years and 4 years, and so on. So there's kind of little differences in the data, and the same thing is when we kind of scale this is the same difference, and then there's like a difference where it's half as much, and then it resumes, and so on. Okay. The next part, it takes all of those things and it kind of creates these squared values. Okay. And basically, so one part, you're going to get this kind of, from this location to this location, you get a linear relationship, and then you'll get a quadratic relationship here. And if you take this vector of x, the quadratic values, and the linear values, the correlation between this and this, you'll have a correlation of 0. Now, if you expanded it further, well, in this case, it would probably still be 0. But and then maybe your cubic term will be something like this. Okay, and the correlation between the squared and the cubic and the linear, the correlation between this and this is going to be 0. Okay, but if you expand beyond this, okay, beyond whatever range you have, now you're going to have correlation between the linear and the cubic term. Okay, so Poly will create uncorrelated values within the range of values that you have for x. So that's what Poly is going to do, and that will allow you to kind of isolate out the second order or third order effects of the of those variables here. Okay, so here I throw in x Poly. And here with x Poly, it only just has the linear and the quadratic component, doesn't have the intercept, the constant over there, and so there's no need to do a 0 plus. And then R will by default fit an intercept term, a coefficient for the first column in Poly and a coefficient for the second column in Poly, which corresponds to a quadratic. And so this is what we end up getting there. And then again, we can ask for our fitted values, and in this case, we don't have to do any multiplication. We can just do $ fitted values, and we would get the same kind of thing. Okay. Now, one of the unfortunate side effects of using Poly is that the x values themselves get transformed. So, when we're looking at this is no longer 1896, 1900, 1904, 1906, and 1908, or anything like that. But they all got kind of turned into these weird decimal values, and so that's what we have. Okay, but using Poly I think is still useful, and we can kind of compare different polynomial fits of different orders, and we can kind of create a whole bunch of these models, compare the different fits. And see, what order polynomial is perhaps the appropriate relationship to explore here. Plug in. Okay. Well, never mind. Up here. All right, so here I'm going to try fitting a third order, fourth order, fifth order, and sixth order polynomial. And so I'm just going to say fit a linear model between, take your x values and make third order, fourth order, fifth order, or sixth order polynomial terms, and try to fit the relationship there. And then here I'm going to plot all of these things, okay? So we're going to first do a linear in red, and then quadratic in orange, third order in green, blue, purple, dark gray, and this is the resulting plot, okay? So the linear fit is in red, And then we get quadratic in orange and cubic in third, fourth, fifth, and sixth order polynomials. And so we can see this, it's trying to fit the data, it's trying to minimize the squared residuals here. Okay, and the question is which of these lines do the best job of predicting our values? Okay, which line is, which model do we select? And so if you took 101A, how would you select something like this? There's a few things you can do, right? One is you can do a ANOVA model, or you could do a likelihood ratio test or something like that to see, you know, was it worth the additional degree of freedom that you spent to include these extra terms or things like that. Early on, I think you learned that if you only look at your R squared value, that will often lead you to the wrong conclusion, because R squared is always going to improve as you add more terms, right? As you make your model more complicated, you're always going to be able to shrink your residuals and improve your R squared. But so now we kind of balance that out by asking, you know, looking at likelihood ratio tests or your F test, and or other things, as you can look at, say, your AIC or your BIC values or things like that. And so here is what, you know, one thing you can do is you look at the summary and you'd say, okay, well, how many stars do I find? Right? This is kind of your base model check. And here, if you do the sixth order polynomial, you get, you know, stars up to the third, but no stars at 4, 5, or 6. So maybe we don't need the fourth, fifth, or sixth order polynomials or something. So that's what we're going to do. Okay. Oh, it says next week. It's today. We're going to look at cross-validation. Okay. So we're going to try to evaluate how well our model fits by using cross-validation. And so let's take a look at what cross-validation is all about. Let me go ahead and give you your second view quiz answer. Today's second view quiz answer is the letter A. A as in apple. A as in apple is your second view quiz answer. All right. So when we kind of take this classical approach to thinking about what is the relationship between variables, okay? It requires some thinking. It requires knowledge about the variables. And sometimes it's just hard to think about this, right? Does it make sense to say the winning race time has a cubic or quadratic relationship to time or the year in which the event took place? Like, what does that mean for there to be a quadratic relationship between time and winning race time? Like, what year it took place and winning race time? And it just feels strange, right? Like, some things make sense, right? There's, like, in physics, we know that like gravity, there's like a inverse squared relationship, and you know, things like with air pressure, and you kind of think about that, and you know, that kind of makes sense. And right, like the intensity of sound, just because, you know, when I speak, like if you're right up next to my mouth, like the intensity is right here, but then as you get farther away, like the energy gets dispersed in larger spaces. So there, you know, it makes sense to have kind of these squared or cubic relationships for some of these things, or inverse square, inverse cube relationships. But then race times, what does that mean? You know, I don't know. So, and then a sixth order, I can't even think about anything in real life that has like a sixth order polynomial relationship with anything. But maybe some of this stuff exists, and I'm sure, you know, we do this, and this is kind of hard, and we got different tools, AIC and BIC, and named after different people and stuff, and, you know, one we have like a log n relationship to kind of the term for how many coefficients we have versus, you know, a 2, multiply that by a 2, and, you know, some will favor simpler models and stuff. On the other hand, cross-validation kind of removes this sort of thinking, okay, this skillful or arbitrary, however you want to think about it, from the decision-making process. It replaces it with a validation strategy. And we just say, well, let's just see how well our model, how well the system works. How well does it perform? And if it performs well, great. And if it doesn't perform well, then let's look for something different. And so what cross-validation will do is it takes all of our observed data and it splits it into basically a training part and a validation, or training and a testing set. And there's several kinds of names and stuff. And if you just took 101C, like, I apologize, you've already heard all of this stuff, but if you haven't, this is an important idea. So we take the available data that we have and we split it into two parts. One part is the training set, and we use this training set to fit the model. Fitting the model just means kind of, at least for linear regression, means estimating your coefficients. It means finding your W hat. It means finding your intercept and your slope. And we take the data that we have in our training set and we try to fit some model to it, okay? And then what we do is, after fitting the model to this training data, the training set, we take those estimated parameters, we take the fitted line, and we say, let's make predictions. Let's make predictions for this other data, okay? This data in the validation set. Now, this is real data. It's part of our original observed data. It's just these data points were not used to figure out our slope and our intercept or our other coefficients. And so what we do is we say, okay, how well does it predict? How well does it predict these new data points that exist? And we use some kind of measure, some kind of metric, and we say, oh, it's the predicted value is this and the actual value is right next to it, so it's doing a good job. Okay. On the other hand, if it predicts 50 and the actual value is 7, and we say, oh, that's a difference of 43, that's not a good job. And we have some kind of measure or a metric to measure how well our predictions are going, right? And so a common choice is mean squared error, or another common choice is this root mean squared error. And we do this for all of our different kind of models, and we compare all of the metrics, and we choose the best performing model. And so we'll look at some cross-validation, but here I'm going to start off with kind of one of the simplest forms of cross-validation, leave one out cross-validation. Now, admittedly, leave one out cross-validation is a little bit too computationally expensive and is not the preferred method, but I think it's the easiest for us to look at and understand, and part of your homework is to write some code to perform leave one out cross-validation. So in leave one out cross-validation, the training data is going to be basically all of your available data, and you subtract off one observation. You leave one observation out, okay? And that one observation is going to serve as your validation set. And then, and you do this, every observation in your data gets one turn at being the validation point. And you're going to have a whole n different training validation sets. And that will give you kind of your leave one out cross-validation score for whatever model it is you're fitting, okay? So I'm going to just illustrate this with a toy data set. And what we're going to do is we're going to figure out what is the leave one out cross-validation score for a linear model fit to this toy data set. So my original data, my x is 1, 2, 3, 4, and my t is 1, 3, 2, 4. Okay, and so this is, did you have a question or just, okay. So this is our data, okay? 1, 1, 2, 3, 3, 2, and 4, 4. And this is what the linear model looks like if we have all 4 data points available to us, okay? All right, but what we're gonna do is we're gonna take this last data point and I'm gonna hide it, okay? I hide this data point. This is now my validation set, and I'm going to fit the line, what is the best fitting line that I have for the 3 remaining points. So for these 3 points. So if I do that, okay, so if I remove, so here I am, I'm covering up that one data point, and I say, okay, fit a model, fit a straight line to the remaining 3. This is the best fitting line for these 3 data points. Okay, you get an intercept of 1 and a slope of 0.5, and this will minimize your squared residuals for these 3 data points. Okay, and so now we say, okay, well, here's my predicted line. How well does it do as far as predicting that one data point? Okay, so the one data point was right here, 4, 4, and we say, okay, how good of a job did it do predicting that? Well, we say, okay, the actual value is 4. This line, which was 1 plus 0.5x, okay, 1 plus 0.5x predicts 3. The actual value is 4. And so we measure that squared error. We measure that error, which is 1, and we square it, and we get a squared error of 1. Okay, so that's one cross-validation value. And I do this for all 4 of my data points. So the next one, okay, so for the code, I'm going to fit a linear model for this, and then I'm going to predict the value, and I'm going to take the difference between what we predicted and what the actual value is, and we're going to square that and add, accumulate our total squared error. Okay, so again, here's our original data set. So now this time, I'm going to hide this point. Okay, so with the 3 remaining points, what is the best fitting line? Okay, so for these 3 remaining points, the best fitting line looks like this: 0.5 plus 0.92857. Okay, and we say, okay, let's put in this 0.32 back in. Okay, so the line, now that I've fit the line to these 3 points, it's predicting 3.28. The actual value is 2. So we get a difference of like 1.285. And if I square that, so the difference is negative 1.2857. If I square that, I get a squared error of 1.65. Okay, and so kind of, again, repeating this, we do this for all of our data points in our data set. So this time I'm going to hide this data set. This one is going to be our data point. This one's going to be my validation set. So if I hide that, this is the line that gets fit. And we say, okay, how well does it do at predicting that missing data point? All right, so here's our data point that was missing. How well did it do predicting it? We get a value of 1.653 squared error. Okay, same thing. Okay, last point. Here's the full data set. We're going to hide this last point. And if we do that, this is the line that fits, the best line that fits these 3. How well did it predict this? This one has an error of 1, square it, and you get squared error of 1. So the total squared error across our 4 things, we had an squared error of 1, 1.65, 1.65, and an error of 1. So we get a total squared error of basically 5.3, and I had 4 data points, and so my mean squared error is 1.3265. Okay, and if I wanted root mean squared error, I would take the square root of this. But basically, this is my mean squared error, 1.3265, and that would be the mean squared error for this particular model, for using a linear model. Okay, now I could try fitting a different thing, and it'd be a little bit awkward, but we could say, all right, let's fit a quadratic model to these 3 points, and we would actually fit those 3 points. And I didn't do that, but we could get that. Okay. Now, R has a function built in. Okay. R says there's a library boot, and if you run library boot, you can do cross validation cv.glm, and this will figure out your cross validation error. And if you follow this code, so you say, take your original data, X and T, this is all data, and predict T based on X, and do cross-validation based on this. It says your leave one out cross-validation error is 1.326531, which is exactly what we got when we did it kind of manually over here. Okay, and so again, just to clarify, you would get basically one single cross-validation score for that entire model, which is usually the mean of the cross-validation errors. And on our toy data set, we got our score was 1.326531. Okay, and this is the score for the linear model. And we might try a different model, say a quadratic model or a cubic model or something, and we'd say, what is the cross-validation error there? Which of these models performs better? And we would kind of make comparisons from one model to another. Okay. Does that make sense? Any questions there as far as how cross-validation works? Okay, so again, the total squared error for the linear for different kind of fits here, we get squared errors, different squared errors here, and our mean squared error for this cross-validation is 1.3265. And we would take the average and we would kind of compare cross-validation scores from one model to another. Okay, we can take cross-validation and expand it and do, say, k-fold cross-validation. So one problem with leave one out cross-validation is that it is computationally expensive. You have n data points. You have to fit n different models. This is going to be... if you have a big data set, 1 million data points, you got to fit 1 million different models, okay? Also, sometimes you want to use cross-validation to get an estimate of what your errors look like, what the tested data error might look like. And again, because all of your models are using pretty much the same training data, if you go from one data set to another, basically all of the data points except for one observation, or I guess two observations, are in common. The resulting data sets or resulting models end up looking very, very, very similar to each other. Your resulting coefficient estimates end up being very kind of highly correlated. You can still kind of overfit the training data with leave one out cross-validation. So when you have larger data sets, it's generally preferable to use k-fold cross-validation, okay? And this partitions the data into k equally or approximately equal-sized blocks. And each block serves as the validation set, and the remaining data combine to be the training data. So this is kind of, if we did four-fold cross-validation, you would take your data, divide it into 4 chunks, and you would train on these 3, and this one would be the validation set. Okay. In iteration 2, you would train on the other 3. This is the validation set. Iteration 4, this one's the validation set. In iteration 3, that's the validation set. Iteration 4, this is the validation set. There's a slightly better illustration. For cross-validation. Oh. All right, and here, this is an illustration of threefold cross-validation. And so here, the original data, there's 30 observations, and we randomly assign them into 3 folds, okay? So 10 points are green, 10 points are yellow, 10 points are blue, okay? So we put them into 3 categories, green, yellow, and blue. And basically, with each of these folds, we take these, again, these are randomly assigned. And so for the first iteration, we'll use the green points as our validation set, and we fit our data on the white and blue points. Okay. Iteration 2, we fit on the blue and green, and we use the yellow points as our validation set. Iteration 3, we use the white, yellow, and green, and we fit on the blue. Okay, so each of the different folds gets a turn being the validation set, and we fit the data on the other data, fit the model on the other data. Okay, so this is an illustration of threefold cross-validation, and what I like about this illustration is it shows that we're randomly assigning the points. Okay, whereas perhaps that's not as clear here, but basically you do partition the data into approximately equal-sized chunks, and you do train on the remaining ones and use one set to be our validation set. So that would be cross-validation. Yeah, question?
So does you do randomize it? Is it randomized each iteration, or do you just randomize it once?
You randomize it once at the beginning.
Okay.
You randomize it once at the beginning to kind of form your 3 different sets, and then you run the validation. So cross-validation, K-fold cross-validation or V-fold cross-validation, whatever letter we're using, is subject to randomness. And so it is often recommended, and I'll show you examples of this, is that you run your V-fold cross-validation or K-fold cross-validation multiple times so that in the beginning you get different randomizations here. Okay, but yes, when you do K-fold cross-validation, you randomly assign the values into basically your different folds once at the beginning, and then you run it all 3 or however many K times. Okay, so let's revisit our Olympic data. We have 28 observations, and what we're going to do is we're going to do some K-fold cross-validation here. I'm going to divide the data into 4 random blocks. Okay, so I'm going to have 7 data points, 7 randomly chosen data points in each of the blocks, and we'll just kind of take a look at cross-validation performance for different proposed models. Okay, and so we'll look at a linear model, quadratic, cubic, 4th order, 5th order, an 8th order polynomial, and then we'll try out a 17th order polynomial just for fun, just to kind of see what happens. And we will calculate the total squared error for each model for each validation set. And we will find the cross-validation score by averaging the squared error for each model, and we'll compare the cross-validation scores to select the model. So the way I'm going to do this is I just randomly shuffle them. Okay, shuffle the numbers 1 through 28, and we're going to assign 7 of them to set A, 7 to set B, 7 to set C, and 7 to set D. Okay, and so I've got 4 different sets. Okay, and this will have all of the numbers 1 through 28 kind of randomly in random order here. Okay, and we're going to kind of store all of our cross-validation squared errors here. So this is kind of this is the code that I've run, right? So basically, I've got 4 different folds, okay? And so here's kind of a big loop, but we're going to take the indexes as designated in our sets. These are the 7 randomly chosen indexes, and that's going to form the index values of my validation set. And I'm going to create my training values by taking the year and subtracting off those validation indexes, and I'll take my training t values and take the time, subtract off those. And then the validation ones will be just those indices. Okay, I'll make corresponding data frames of the training data and validation data using the training x's and training t's and validation x's and validation t's. Okay, and then I will create a model. I'm going to create a linear model to predict t based on x using my training data. And then with this model, I'm going to make predictions for the validation data. and this will be my predicted values. And then I take the actual values in my validation data, and I subtract off my prediction values. I square them, I add them up, and I divide by n. That's going to be my kind of the mean squared error for that one validation set. I do the same for the polynomial or quadratic model. This time, model 2 is predict t based on a second order polynomial of x using the training data. Once we have that model, we make predictions using the validation data. We get our predicted values, and then I'm going to get the quadratic, I'm going to get the squared error by taking the actual data, subtracting off our predictions. We're going to square them. We add them up, divide by n. Okay? Does that kind of make sense? What this code is performing? And here we're doing a whole bunch of different fits, and so I've just shrunk the font, and you can see I've got poly 2, poly 3, poly 4, poly 5, poly 8, poly 17, so on and so forth. But that's basically what I'm doing. And to each of these, I'm just adding my mean squared error to each of these kind of cross-validation vectors to kind of keep track of everything. Okay, so let's take a look at how this actually performs. So here is the data, and my 7 data points in this particular validation set. So I arbitrarily chose validation set C, and these 7 points in red are the validation points. And so we're going to say, okay, let's remove these 7 red points. So this is the training data, and let's fit a line, straight line, to this training data. Now that I've fit a straight line to the remaining 21 points, we're going to say, how well did you predict on the 7 points? Okay, so these are the 7 validation points, and we can say, oh yeah, you know what, some of these it predicted real well, right? These 4 data points ended up like almost exactly on the line. These 3 had a little bit of error, and so anyway, we calculate this squared error for each of these things, and we'd say, what's the mean squared error on this validation set? We get 0.0319. Okay, we'll do the same thing. So again, kind of going back to this data set, I'm going to take those 7 points away, and we're going to fit a quadratic model to these 21 points. And we say, how well does this blue line fit the 7 points in my validation set? And this is what we get. Okay, so kind of compare this versus this. So the red points are in the exact same location, it's just the blue line changed. Right? And so now we have different amounts of error, and the mean squared error here is actually 0.025. Right? And you feel, oh, this actually looks like it's doing a better job. But it turns out, you know, the thing about mean squared error punishes big differences a lot heavier than small differences, right? So if you're off by 0.1 and you square it, your mean squared, your squared error is 0.01, okay? If you're off by 10 and you square it, your squared error is 100, okay? So it would much rather make a bunch of these mistakes of 0.1, because those only count as 0.01, than to make, you know, one mistake of 10 somewhere along the way. So mean squared error punishes big mistakes heavy, and small mistakes punishes very little. So even though these are like a bunch of little mistakes, it's almost like hardly anything. Okay, so that's what we have there. Okay, let's try the cubic fit. So again, we go back to the 21 data points without our 7 red points, and we say, all right, what's the best cubic fit that we have for these 21 points? And this is what we get. Okay, and we go, this looks suspicious already, but we'll try it out, and actually it performs very well on this validation set. Okay, for this validation set, we'll get mean squared error of 0.0131. Okay, What about the fourth order? Okay, fourth order looks like this. Again, it's being fit to the training data, 21 data points over here. And we're going to say, how well does it perform on your 7 points in the validation set? Okay, and this is what we have here. Here it is for the 8th order polynomial being fit on the training data. So you can see the 8th order is able to accommodate this one kind of outlier out here. And we're measuring the error. Okay. All right, and again, just for kind of laughs, we fit the 17th order polynomial, right? And so with the 17th order polynomial, we have a high amount of flexibility, and we fit in our training data, we fit some of these points like perfectly well. Okay, our prediction line performs very well, and really minimizes kind of our squared errors here. And we got, just a tiny bit of error, but again, means squared error doesn't really care about tiny amounts of error, and so it fits these very, very well. How well does it predict my 7 red points? Okay, these are my 7 red points, and we can see it does a really bad job for these points, and this point it does absolutely terrible, right? Because when you have x to the 17th power, going from say 1 to 2, you're going from 1 to the 17th, which is 1, and 2 to the 17th, I have no idea. It's a huge, huge, huge number, right? In the millions or billions, I don't know. Okay, and so this small difference, now we have this huge error. And so the mean squared error on this validation set is this comically large 1,640, okay, compared to the mean squared error over here is like 0.02 and 0.01 or something like that. So this 17th order polynomial, perhaps if we looked at the mean squared error here, is small, but when we check it on the validation set, it's a ridiculously large value. Okay, and again, this was just for one validation set. We had a total of 4 validation sets, and I don't have the plots for all of them because it's pretty much the same kind of picture. It's just slightly different lines, slightly different amounts of error. So, but this was just one of the 4 validation sets, and we would run this kind of thing, and we would calculate, okay, what's the mean squared error on this validation set, mean squared error for this validation set, and we would do it for all of the things. And so I think this one we were looking at validation set C, and so, our mean squared error is 0.0319, here was 0.025, 0.0131, 0.0192, and so on and so forth. And we can see, yeah, for validation set C, this is the values, 0.0319, 0.025, 0.0131, 0.0192, so on and so forth. These are the cross-validation sets. And I went through and I calculated the mean squared error for all of the different validation sets. I had validation set A, set B, set C, and set D. And when we calculated the mean squared error for each of these things, we got different quantities. And so the overall cross-validation score is the average. Okay, the average, I got 0.0224, 0.0258, 0.0319, 0.1896, and the average is 0.0674. And I calculate the average for the different models that I checked. Okay, and so looking at the cross-validation score, the one with the smallest average here is the 8th order polynomial, 0.0419. Okay, and then the next best performing is the 3rd order polynomial of 0.0571. Okay, now we think, okay, well, what's going to be the best thing? Again, cross-validation, V-fold or K-fold cross-validation is subject to the initial random assignment of points. Who ends up in which of these different folds and how those values perform. And so, it's often recommended to just try out, say, a different seed. And so here I tried a different seed, set seed 7, and I ran kind of the same process. And so some of these things, we got really big errors. And this time, the 8th order polynomial doesn't perform as well, 0.096. The best performing model here is the 3rd order polynomial of 0.0464. And here, if I try out another random seed, this time the best performing polynomial, again, is the 3rd order polynomial, smallest cross-validation score. So if you have the computational power to run k-fold cross-validation a couple times, we recommend doing that and measuring your cross-validation scores. And if multiple of them agree and say this is kind of the best model to use, then that's a good indication that might be the best model to use. Okay, so in this case, the 3rd order polynomial ends up performing the best. Okay, does that kind of make sense as far as how cross-validation is working? And you have kind of exercises in your homework where you have to kind of code up your cross-validation. Okay, let me give you your last view quiz answer already. Last view quiz answer is the letter A. A as in apple. A as in apple is your 3rd view quiz answer. Okay, 3rd view quiz answer is A as in apple. And you should be able to, I guess, finish the quiz now if you want. If we want, you can do cross-validation using library boot, or if you have, if you've taken 101C, then I covered tidy models and using cross-validation there to kind of evaluate your model performance, and there's different kinds of things. In your homework, you'll be kind of coding, writing loops and stuff to kind of perform cross-validation, and I give you a framework to, I think, hopefully to help you code some of this out. But again, I think there's merit and learning value in kind of coding up these tasks yourself. But again, in a professional setting, you wouldn't really do it yourself. You would use a professional package out there. Okay, so you have cv.glm that can be used to perform cross-validation. You can specify the number of folds, and if you don't, it's going to default to leave one out, cross-validation. And so I'm going to perform cross-validation a couple times on each model, and what we will see is that there's going to be some variation between the different runs because the random blocks that get created in the beginning, again, who gets assigned to which of the different folds changes every time we run it, and therefore the scores that we get will be slightly different. So here, I do 4-fold cross-validation, and when I run this using a linear model, these are the different cross-validation scores I get: 0.064, 0.0659, 0.0576. Okay. Here, if I do a quadratic model, my cross-validation scores vary from 0.062 to 0.0469, or 0.47 to 0.0648. Okay, again, a little bit of variation here with 4-fold cross-validation. However, and here it is on a 3rd order polynomial, again, slightly different values. And so, when you have values kind of overlapping each other, it might be a little bit tough to be able to really tell, is the quadratic or the cubic model a better fit? And it's a tough call in some of these situations, right? You might have to run this multiple times. But if you do leave one out cross-validation, no matter what model you're using, you're going to get the exact same values. Okay? Because with leave one out cross-validation, there is no randomness. Every data point in your data set gets to be the validation set exactly one time, and the validation sets are all identical. It's every single one of those observations. And so your leave one out cross-validation is not subject to kind of randomness, and so you're going to get the same value every single time. Whereas over here, the other kind of k-fold, k anything less than n, you get the effects of randomness here. Okay, we'll end a tiny bit early today, but basically cross-validation is a method for us to kind of evaluate how a particular model will generalize or perform to new data that wasn't used to train it. And the goal of cross-validation is simply testing the model's ability to predict new data. Okay, it doesn't tell you if the model actually makes sense, right? Because the cross-validation might say, hey, this fourth order polynomial is the best performing model, and you go, well, does that make sense? And it says, I don't know. It doesn't really care. That's not the point of cross-validation, right? With a lot of times when you make a linear model, you're trying to say, you're trying to reason about your variables. Cross-validation doesn't care. It's just trying to measure how well is it performing. And it's generally recommended to perform multiple rounds of cross-validation, and it's performed on different partitions, and then you generally average them together to kind of get an estimate of the model's predictive performance. Okay, we will end here for today. Have a great weekend. We will see you next Tuesday. Good luck as you work on your homework, and we'll see you then. All right, that's it for today.